we've now already looked at two basic methods for adding vectors together. The first was just to draw them in a perfect scale diagram and then figure out what the addition vector would look like strictly by measurement. We also drew our diagram sort of roughly to scale after that, and then we're able to solve for the new vectors just using geometry. But there's a third way, and it's perhaps the most powerful that we can add vectors, and it involves something called vector components. And we've already seen so far that our vector calculations become a lot easier when, first of all, the vectors go in the exact same direction. And when they don't go in the exact same direction, it's still easiest if they at least go along an axis line. So if we're dealing with vectors that are, let's say, straight north-south or straight east-west. What becomes the most challenging is when we've got a vector like we have here with vector A that's on an angle. So in this case, vector A is just 5 centimeters long, but it's on an angle to our direction axis. It's east 53.1 degrees north. And those are the kinds of vectors that are trickiest to add with other vectors. So we're going to use a component method to try and deal with it. So to find the components, we need to ask ourselves, what two smaller vectors that go along the axis lines could we add together to make up this final vector? And if we scroll down a little bit, we can see how we could actually make that happen. So we can actually find these new vectors by just drawing perpendicular lines from the axes to the tip of the original vector, the main vector. So you'll notice that this is just vector A, the original one that we started with. But there are these two new vectors that we've drawn in here. So the first one that goes along the y-axis we call the y component vector. And so that's the y vector, and I'm going to put a little vector arrow on top to remind myself that that is still a vector. And we call that the y component. The x component of this vector is this line that we've drawn straight along the x-axis. We call that, again, the x component. And now, if we think about this for a moment, we can see why we refer to these as components. In general, that word component just means two smaller pieces that when we put them back together equal one larger original piece. And in this case, when we take these two smaller vectors, the x and the y vectors, and we add them back together tip to tail, they add back together to produce the original vector A. And we can verify that below. So in this case, we can see that this would be what would happen if I added vector x and then vector y. I still get the original vector A that I had before. So this version would be like if I had x and then added y. And when I add those tip to tail, I get the original vector. But I didn't have to just do it in that order. When I took the vector y first and then added it tip to tail with the vector x, I still get the original A vector that I started with. So this would be the case where I added y and then x. But what I'm trying to show here is that either way, no matter which order I add these two vectors in, those two component vectors add back together to produce the original vector. So that's what that word components means. It's two smaller vectors that add back together to produce the original one we started with. So the follow-up to that is, okay, why did we spend so much time trying to find these two smaller vectors? Well, again, these smaller vectors are special ones. They're vectors that go straight along the axis lines. And so that makes them really easy to work with. Because even if we've got some vectors that go south and some vectors that go west, when we put those together tip to tail, it'll still produce a nice right-angled triangle, something that's easy for us to work with. We can now think about how we would actually mathematically come up with what these components should be. And because we end up drawing little triangles, just like we've been doing all along, trigonometry is going to become a big component of this. So let's think first about the x component. Now, that x component, of course, is this one along the x-axis. And right now, we also have the y component drawn over here. But I'll just remind us that we could take this vector and move it over here, and I could draw the y vector over here. So really, this is like my x vector, and I'm going to draw my y vector over here, just so that I can show that it completes a nice right-angled triangle. And in dealing with that right-angled triangle, I can use trigonometry now to figure out how long each of those two sides are, because my x and y components are really just the sides that are opposite and adjacent to the angle that I already know, which was the 53.1 degrees in there. So if I want to find the x component, let's think about what trigonometry would tell me. Well, let's say I don't know what that angle is. I'll just call it theta for now. The x component I would have to find using what I know about cos. I know that cos of some angle theta is its adjacent side divided by its hypotenuse. So specifically in my case, the adjacent side would be this x component that I'm looking for, and the hypotenuse is actually just the original vector that I wanted in the first place. So doing adjacent divided by hypotenuse for our triangle just means that I want to take the x component, however long it is, and divide it by however long the full a vector is. So that actually tells me something else, because what about if I, instead of trying to find cos theta, what about if I actually want to find this x component itself? Well, I just do a little rearrangement. So what this tells me is that the x component I can just find by taking the original vector a and now multiplying by cos of the angle. So if I want to plug in some specific numbers in our question, remember the length of vector a was 5.0 centimeters times the cos of 53.1 degrees. And when I do all that, it gives me approximately 3 centimeters. So the x component would be a vector that goes straight along the x-axis from left to right and is exactly 3 centimeters long. And now let's try and use some trig to find the y component. So the y component I can analyze using sine ratio. And sine tells me that sine of some angle theta is its opposite side over its hypotenuse, which in my case now is going to be the y component, because that's the opposite side, divided by the hypotenuse, which is still vector a. So again, a little rearrangement, because what I really want, if I want the y component, is to know how long is this vector here. So what that means is the y component I can find by taking my original vector once again and now multiplying, but instead of multiplying by cos, I'm going to multiply by sine of the angle. So I'll plug in the specific things I know, 5.0 centimeters times the sine of 53.1 degrees, and just underneath I'll jot down that that's approximately 4 centimeters. So what this is telling us overall, once again, is that if we take a vector that's 3 centimeters long and goes straight along the x-axis, and add that tip to tail with a vector that's 4 centimeters long and goes straight along the y-axis, those two vectors add together to produce one overall vector that's the exact same as the original vector a that we started with. We can take our results here and try and use these to generalize an overall pattern. So what we're seeing here is that we can find the x component by just taking the original length of the vector and then multiplying by the cos of the angle. We found the y component in a very similar way. We took the original length of the vector, but instead of multiplying by cos, we ended up multiplying by sine of the angle. And in fact, any time you're dealing with a vector that's angle is given the way that we were given this one, in this case, this would be the angle that it makes with the horizontal. So the vector angle that we're given is between the vector and the horizontal line. Whenever that's the case, you can find the x component using cos and the y component using sine. But it's useful to know that if our angle was ever given with the vertical, meaning that we knew, let's say, this angle in here, instead of the 53.1, if we were given that green angle, then we would actually use sine to find the x component and cos to find the y component. So just for the sake of your notes, let's jot that in. So if your vector makes an angle with the vertical, sine and cos will switch. So the sort of shortcut to remember when finding components of a vector is that you'll always just end up taking the original length of the vector and either multiplying it by the cos of the angle you're given or the sine of the angle you're given. And whether you use sine or cos just depends on which way you were given that original angle itself. So let's take a look about how we can use this in a specific problem to actually help us with vector addition. Using components now allows us to take any vector that we're given and break it down into something that either goes along the x-axis or something that goes along the y-axis. And if things only go on the x-axis, then those things can be easily added up. If things only go along the y-axis, then those can easily be added up. And so that's what we're actually going to do. We're going to take any vectors that are on angles, break them into their components, and add their component parts together, instead of trying to add the entire vector all in one step. So let's see how we can do that in a specific example, like this fishing ship. So I'll start by drawing a beautiful diagram of a ship. That's my beautiful ship there. And it leaves St. John's Harbor and heads 27 kilometers straight to the east and 40 kilometers south, 10 degrees west. So before I get too far into this with my directions, I should make sure that I put a direction axis on here. I'll use pretty standard directions, north, east, south, and west, but I'm also going to label that north will be positive, and anything I do to the east I'll consider positive as well. So that means west and south, those directions will be my negative directions. I'll use my line tool to draw some nice straight vectors for myself. So we have a 27 kilometer vector that needs to go straight to the east. So something like that. And then a vector that is longer than that, 40 kilometers long, that is south 10 degrees west. So it should be coming down, but at some kind of an angle a little bit towards the southwest. So I've exaggerated that 10 degrees. That's probably much more than 10 degrees towards the west, but I've exaggerated it just so it's a little bit easier to see. And then I'll use a dotted line for my overall displacement. So remember, my total displacement, or final displacement, means if I go back to the original starting point of the ship and I go straight towards that final ending point of the ship, that dotted line is what I'm trying to find. That's my final displacement vector. From here, it's also useful if we label some of these vectors. So the 27 kilometers I'm going to just refer to as D1, the first piece of the displacement. The 40 kilometer vector I'm going to call D2. And so when I label those, I'm going to call this one D1. I'm going to label this one D2. And this third one I'm going to call DT, or total displacement. It's another way of saying final displacement. From here, it's useful if we break things up into a chart form. And you won't always have to use a chart for a question like this, but it can just be helpful to organize all of the different pieces of vectors that we're going to be dealing with. So in this chart, I'm going to have one nice big column for all of my x components, one nice big column for all of my y components as well. And then the rows will be one for each of the vectors that we're dealing with. So for my first displacement, it gets its own row, and that row doesn't need to be very large. The second displacement, though, give yourself lots of room in that row, because we're going to need to actually do some calculations in there. And then the very bottom row is where your total is going to be. So I'm going to call that dt once again. That's my total displacement. And that's what I'm going to try and find for those total displacement vectors. So when I try and set up this chart, what I need to do is look at each vector and ask myself, what component of this vector goes straight along the x-axis, and how much of it goes straight along the y-axis? So for the first vector, actually, d1, that's pretty easy to do. And in fact, we don't need to do any of the trigonometry that we talked about in our previous steps. Because in this case, d1 is straight along the x-axis already. It's 27 kilometers straight to the east. So when I ask myself how much of that vector goes straight along the x-axis, well, 27 kilometers of it does. The entire vector goes along the x-axis. And then when I ask myself how much of it goes in the y direction, 0 kilometers of it goes in the y direction. There is no north or south in that first vector. So that's really all I have to do for the first vector, but I'm going to be a little bit more redundant than that, and I'm going to say that it's positive 27 kilometers, just to remind myself that in reality, that's actually going in the positive x direction. If I called that negative 27, it would mean that you're going 27 kilometers straight to the west. For D2, now I need to actually break things up a little bit and find their components using some trigonometry. Well, I'm going to add a little bit to my diagram to show you what kinds of calculations we're really going to be doing, what it is we're finding here. So what I need to find is how much of this vector is going straight downwards in the y direction, and how much of it is going straight from left to right in the x direction. So those new green vectors that I've just drawn in, those are the smaller components of D2. And in fact, I can even label them if I want to. So just to give myself a bit of room, I'll label them down here. So this one on the side is technically D2y. It's the y component of my D2 vector. And this one here, I can call D2x. It's the x component of my D2 vector. So what I want to find is how long each of those vectors are, and then that will make it easier to combine them with D1 in the first place. But to find those vectors, that's where I need to use some of that trigonometry we talked about before. So first, I want to find the x component. Well, that's the one that I just called D2x. That's what I'm trying to find. Well, in order to do that, we know that we always take the original length of the vector, so I'll take the length of D2 itself, and then we just need to multiply by either the sine or the cos of the angle that we were given. Well, the angle that we were given was actually this angle in here. So the 10 degrees is actually that little angle in there. And the side that we want right now is the x component. And the x component is on the opposite side to that angle. So you have to ask yourself, out of cos or sine that we have to choose from, which is the one that uses the opposite side? Well, the one that uses the opposite side is sine. So we're going to take D2 and multiply by the sine of the angle that we were given, which I'll call theta for now. In my next step, though, I'll plug in what I know. So in this case, it's 40 kilometers multiplied by the sine of 10 degrees is what we specifically have. And so I will just approximate that to 6.9. On the other side of things, if I want to find D2y, well, now I know it's going to be D2 times the cos of theta. And I can check that that would be cos theta because now I'm looking for the y component, and the y component is adjacent to the angle that I was given. And out of sine and cos, the one that uses adjacent is cos. So now I take my 40, I multiply by cos of 10 degrees, and I get approximately 39.4. So those are the actual numbers that I would get when I punch all this into my calculator. But once I get those numbers, there's one extra step I have to do each time. So that's when we need to step back and say, even though these are the numbers that we got, should these numbers actually be positive or negative? And that's going to depend on which direction the components are pointing. So the D2x component is actually pointing straight west. And west is the direction we said was negative. So even though my calculator just said 6.9, I need to use my diagram to realize that this should really be negative 6.9 because it's going in the west direction. At the same time, if I think about the y component, it's going straight south, actually. And so south is also negative. So this 39.4 should actually be negative 39.4. So again, your calculator won't tell you that. But because we know that it's going in the south direction from our diagram and from what we know in the question, we insert that additional negative sign to make sure that we know it's really in what we've called the negative direction. But what's nice about this component method is once we've set up our table in this way, we can find the total x component and the total y component by just adding up the columns. And when I say adding, I mean straight addition, but we have to be careful that sometimes we'll be adding a negative. So if I take, for example, 27 and I add negative 6.9, I get a total x vector of positive 20.1. When I take my y components, I have 0 from D1, and I add that with negative 39.4. We should be able to do that math pretty easily. We get negative 39.4. So now what we've done is find an overall x vector and an overall y vector. And that gives us some special meaning. It says that even though this ship originally went 27 kilometers east and then 40 kilometers south, 10 degrees west, we can take all of that motion together and think of it as really the ship went about 20.1 kilometers east and then straight south 39.4 kilometers. In the end, that's essentially what the ship actually did. And so it doesn't matter what the individual vectors did along the way. All that really matters is what was the total horizontal displacement, meaning the total x displacement, and what was the total y displacement. And now we found those. But we don't want separate x and y components. In the end, in our final answer, we want to put those components back together. But what's nice is they're components that are pretty easy to add back together. So we can't just add them like regular old numbers anymore. We now need to add them in a tip-to-tail fashion. So we take the positive 20.1 and the negative 39.4, and we draw a new tip-to-tail diagram to represent this. So positive 20.1, if I just do a quick sketch of this, that would be a vector that's going straight towards the east. And the 39.4, that negative just means that it's going straight down. So I should just draw a vector that adds tip to tail with that, goes straight down, and its length is about 39.4 kilometers. That's the length of the vector. The negative, remember, just meant that it pointed down. So those added nicely tip to tail. They meet each other at a nice right angle. And all I need to do is go back to my original starting point and find how long this dotted line is that goes straight to my new ending point. Once I find how long that is, that'll be the total length of my displacement. And then I'll just also need to find this angle in here to find what direction the ship has turned in. So it'll be some direction turning from the east towards the south. So some southeastern direction, but we need to find theta to do that. So from here, I'll let you guys try and finish this off in your notes. And then we'll take up example 2 in total together. But you can go ahead and try example 2 if you'd like, which is just doing a similar process, only dealing with forces instead of displacement. If you're a little bit stuck trying to finish this problem off, just remind yourself that you can use Pythagorean theorem to find the length. And you can also use tangent ratio to find the angle. So take a stab at doing at least that on your own and try and finish off this first problem. And then if you're feeling confident in this stuff, see how you do with the forces in example 2. But as I said, we'll take all of this up in class in more detail.